We're going to take just a minute to take a closer look at filters. Now, filters really are these kind of round, plastic colored pieces. It's almost like looking through colored cellophane, except filters are made more precisely. And they serve a variety of purposes in astronomy. In particular, here's a filter set that an amateur astronomer might use, and it's what's called a lunar and planetary filter set. And so this is something you'd use so you could see the planets through your telescope with greater contrast. You might look at the moon and be able to see its craters better than if you weren't using filters. Now, professional astronomers use filters in order to measure specifically certain wavelengths of light that are coming from distant objects. And we'll see some of the ways in which that plays into astronomical research. But one of the immediate benefits to us is that when we use red, green, and blue, we can actually make true color images. You'll see this filter set wouldn't serve that purpose because it doesn't have a green filter. You need red, green, and blue to do true color. I want to take a look at this simulation with you, which shows us in greater detail what this really looks like. So let me walk you through this a second. What we have here in this bottom left-hand corner is our source of light. And this is represented right now by this straight line, where we're saying the intensity of light is what's measured here on the vertical axis, and the wavelength of light is here on the horizontal. Right? And we know that wavelength relates to color, so it shows the visible range of the spectrum with violet through red, here so that we can see that for reference. Now, this particular object is glowing uniformly in all colors. And no object actually does that in reality. But this is a hypothetical object. All wavelengths of light, it's glowing at the same brightness. Up here on the left, it shows us what that would look like. In this case, it's sort of a gray. You might say, well, why isn't it white? If it's all the colors of the rainbow, it should be white. And it's like, yeah, but we're not at full intensity, so it's kind of like a gray color. Now you see here is this source. That's the thing where it could be a star or a planet. That's what we're creating here, this source of light. And you can see here there's a filter rack. And then there's a detector. That's our camera. And so this simulation allows me to put various filters and see what we're actually going to detect if the light passes through those filters. You'll see that illustrated up above with sort of like a mathematical equation, which is saying the emitted distribution, that's how the intensity is distributed versus wavelength. It's all uniform. And then we'd multiply that by the filter transmittance, right? So it's saying, well, what wavelengths of light does the filter let through? So let's just look at this as an example. If I click on visual, and I picked a confusing one for starters, sorry about that, but visual is the word that astronomers use to represent green. So we don't actually use the word green, sorry, we use the word visual. Okay? And you can see that this filter, it doesn't let through only green light. It's not like a narrow filter that only lets through just the greenest of green, but it lets through a range of colors around green, centered on green. So it does let through some red light, and it does let through some blue light, but mostly it lets through the green part of the spectrum. So if we were to take this green filter, this visual filter, and put it up here, you kind of see what happens, right? And just like you'd expect if you took a green piece of plastic and put it in front of a white light bulb, you'd see that it would look green. So what was sort of a uniform gray-white color now becomes this detected color of green. And we can see that this emitted distribution multiplied by our filter transmittance means that what we get out ultimately is this sort of mirror of our filter, right? We're only seeing the wavelengths that passed through our filter. So as you can imagine, right, well, what would happen if I took a blue filter? Let's just see what this blue filter looks like. So in the bottom right-hand corner, you can see the wavelengths that the blue filter lets through. It lets through some violet, some ultraviolet, but again, primarily blue. And so if I added the blue filter here, we could say, well, what would happen to the light that's passing through? Well, I'd look at the blue filter, I'd look at the green filter, and I'd say, do they overlap? Is there any region where the two filters overlap each other? It looks like right around 500 nanometers, they both let through a little bit of light. So maybe there's a small region of light that could pass through both of these filters, right? Because the green filter is blocking everything below 500, and the blue filter is blocking everything above 500, but right where they overlap, let's see. So I'm going to add both of these filters. Maybe you can see there's the tiniest bump right there, right? Very small little bump of light that's being let through. That's our combined filter transmittance. And so you can see we've got basically no light left over here at the end. So that's a bad move. Let's take out that blue filter. Maybe our red filter. Let's see what would happen if we combined our red filter with a green. Now looking at it down below, here's our green filter. I can see that 600 nanometers, there's a bit of red light that gets in. Let's see, and our red filter extends down to about 550. So I'd expect there's a little more overlap here. Let's see what happens. Yeah, I can see there is a little more overlap. So what was white has now become kind of a brownish color. Now, of course, in practice, astronomers would never do this because we're blocking out all the light. But if we want to select specific wavelengths, this is the way we could do it, using these filters. Let's just see what the ultraviolet one looks like. Here's ultraviolet way down here, 300, 400 nanometers. Put that on there. Of course, I'm not going to see it. The detected color is not something I would see with my eyes, but a lot of digital cameras can still detect the ultraviolet light even that our eyes can't see. One interesting filter I want to point out is the atmosphere is listed here. And you see this is a very unusual filter, right? It blocks everything below 300 nanometers and gradually lets more and more light through. You see the closer we get to 100%, the more light it's letting through. It lets through most of this visible range of the spectrum, and then it's got several dips in the infrared, and we'll learn more about that later, but this acts as a filter. Our own atmosphere blocks certain wavelengths of light. And so we could add that up here, and we'd see that what was white now looks a little bit orangish, right? Because our filter here tends to block a little bit more. The atmosphere blocks a little bit more on the blue side than it does on the red side. So it's using filters very much like this that astronomers select out the light they want and can ultimately go about constructing color pictures when they bring these digital images together on the computer.